Okay, so in this video, we're going to be talking about an alternative notation for the derivative. Now, when I say this, I mean, like, it's going to be a different way we write the derivative, and it's going to be a different sort of approach that we're going to be taking. And this video is more of an explanation on why we've come up with this type of notation, okay? So there's going to be no examples in this video, but it is just an explanation on why we get the form to y dx. So let's start off with a point. So let's let P be some point, okay? And it's going to be any point on the graph of a function. And we're going to have a look at a function that I've drawn in a little bit, okay? What we're going to do is we're going to let x change, okay? So as in we're going to move it along the function. We're going to move it along the function a small amount by a small amount. By a small amount to x plus delta x, okay? Or we would just say dx. And what we're going to do is we're going to also let y change by the same small amount, by a corresponding amount, okay? Corresponding amount, delta y, wow, that was horrible. Okay, lowercase delta, not capital delta, delta y to delta, or it's going to be y plus delta y. Now, I'm going to show you, okay, so, well, let's have a look and see what this means, and we'll come back and continue on in a sec. So, as you can see, over here, and I'm going to use purple to indicate parts I'm going to drawing. Okay, so we've picked some point over here, and we're going to let that point be xy, okay? So it's x along the x-axis and y along the y-axis, okay? Okay, and we've got a second point q, okay, which we've moved this x some amount, we don't know, but we've moved it x plus delta, okay? So, or delta x, so like, you know, so say delta is like, you know, 0.02, so if we multiply that by our x, it's going to move us, or maybe like 1.02, I should say, it's going to move us a little bit in that direction, okay? And we've done the same in the y, okay? So this y going up here, okay, we've changed it delta y. And so our new point at q is made up of the x plus that little change I've made in this direction going this way. And the y is, you know, y plus that little change in y that I've made going up, okay? And that was too much. So those little changes that we've made, we can, you know, work with, okay? So we've got our tangent going on a P, and we've got our P at Q. So what we're going to do is we're going to state that we've got a second point, you know, our second point, Q, is a second point on here, which is at the point x plus delta x, y plus delta y, okay? So x plus delta x and y plus delta y, okay? So the gradient, okay, so the gradient, our rise over run, okay, becomes, so it's going to be our q, well, let's use q first, so let's do it this way, x2 minus, no, sorry, it should be y2. So it's the difference in the y's over the difference in the x's, okay? So y2, so let's say this is y2, this is y1, so this is, x2. So that's our second point. Our first point is this one up here. Okay, so if we substitute those into here, we get, we get y2 minus y1, so that's y plus delta y minus y over x plus delta x minus x, okay? So the y and the y cancel out, the x and the x cancel out, and so we get this gradient is equal to the little change in y over the little change in x. Okay, so our gradient is, so how, depending on how small we make that little change, so depending on how much further we go in these directions, okay, we can define our gradient as that little change that we've made. So the little change in the y over the little change in the x, okay? So once we've done that, we could, once we've done that, okay, what we can do is we can start reducing and reducing and reducing the distance between these two. So I can start moving Q closer and closer and closer and closer to P and getting this really, so that my secant starts turning into the tangent, just like we did before. So what we're going to do is we're going to start taking a limit. So I'm going to say when delta x is small, the secant PQ is almost the same as the tangent at P. And the derivative is the limit. Okay, so the derivative becomes a limit. Again, remembering our limit is when it gets smaller, smaller, of delta y over delta x as Q gets as close as we like, or as we want it to P. So that is delta x is going to be approaching 0. Okay. So to summarize, we're going to let dy be the small change in the y resulting from a small change in the dx in x. So then our terms dy over dx is going to be equal to the limit as delta x approaches 0 of dy dx, because it's going to be changing at the same rate. So it's important to say that the derivative dy dx is not a fraction, okay? So this is not a fraction. It's terminology, it's not a fraction. However, the dy dx, or the delta y delta x on this side, the limit of it is a fraction. But the limit of a fraction, dy dx as dx approaches 0, okay? So what we can now start using is whenever we want to find derivative, or whenever we want to use the derivative, so normally we said f of x is equal to x squared, and so then f dash of x is equal to 2x. Say we're using y, so instead of a function, we're using a graph. So we can say dy dx, okay? So the derivative at y is equal to 2x, okay? So it's just different notation that means pretty much exactly the same thing. And this explanation, which is not really necessary to use it, is just the explanation on why we get it. So just think, if I push this q value here really, 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 really close to p, okay, so that it changes the value. So, this value gets closer and closer and closer and closer and closer. And, the closer and closer and closer I get, I'm using my gradient, my dy dx. So the closer and closer and closer that this gets to 0 is going to give me it's going to give me a really good understanding or idea of what my gradient is going to be. So as that approaches 0, this approaches 0, and it's going to give us our derivative. Okay, so with that being said, that's the explanation-y part of what this is. In this topic, we're going to be looking at a few things. So what we're going to do is we're going to be looking at, we're basically going to have another explanation video on the second and higher derivatives and operative and treating ddx as an operator function. Okay, we're going to be using dy dx notation. We're going to be finding tangents passing through a fixed point and families of curves with the same derivative. Okay, so with that being said, we're going to look at that shortly, and I'll see you in the next video.